Welcome to the video lecture on evaluating limits algebraically with limit laws. Up to this point, we've already discussed two different ways to find limits. One way was to do it numerically using a table of values, and one way was to do it graphically by considering whether or not two cars would crash on our graph. We're going to learn a third technique today, algebraically finding limits using some theorems or limit laws to help us do that. Now, there are some general situations in which it is easy to find a limit by just plugging in c into your function, where the limit as x approaches c of f of x would just equal to f of c. And we call that direct substitution when we just plug in c for x. Let's look at three cases where direct substitution works for finding a limit. The first example would be for a very basic function, a constant function. B here represents any constant. So imagine if you had a function f of x which was always equal to b. That would be like having y equals to b. What would the graph of that look like? Well, a constant function, like y equals b, is a horizontal line. So this would be just the graph of a horizontal line at a height of b. So suppose we picked any value c, and we looked at the limit as we approach c from the left and from the right. Hopefully it's obvious to you that these two cars would crash, and the height at which they crash at is just this height b. So we could say that the limit as x approaches c of this constant function is just equal to that constant right back again. Does it matter what c I choose? No. The limit of a constant is equal to that constant regardless of what c you look at. Okay? Now let's make our function slightly more complicated. Let's let f of x be equal to x. Well, that would be like the line y equals to x, and the graph of y equals to x is just a linear function. It has a y-intercept of 0 because there's no constant on the end, and the slope is 1. So that's just a diagonal line right through the origin that has equation y equals x. Now, because we're on that line y equals x, every x point on this graph has exactly the same y. So x's are always equal to y's. So suppose we look at the limit as we approach any random c, then from the left and from the right, again, these two cars are going to crash. What height is this that they're going to crash at? Well, it would be whatever the y-coordinate of this point is, and since the y's are equal to the x's, and x was c, then this must be c as well. So what that tells us is the limit as x approaches c of just x is equal to c. In other words, we can just plug in c for that x. Alright, now let's look at the limit of a power function. So something like x to the n. Now it kind of depends on whether n is even or odd as to what the graph would look like. If n was an even power, then the graph of x to an even power looks kind of like a quadratic or a U shape. If the power n was odd, then it would look more like a cubic function, something like this. Now, regardless of which graph we're on, if I pick a random c and I approach from the left and from the right, you can see from the graph that the cars will crash, and it will crash at a height of whatever this point is. And since these are on the function y equals x to the n, when x is c, that makes this height c to the n. So what we can tell graphically is that this limit as x approaches c of x to the n is just c to the n. In other words, we get to plug that c right in for x and we'll have our answer. So let's formalize this into our basic limits. So suppose that b and c are any constants, any real numbers, and let n be a positive integer. Then what would be the limit as x approaches c of a constant b? That was our first example up here. The limit of a constant is that constant right back, and it doesn't matter what c is. So in other words, the limit of 4 has to be 4, and it didn't even matter what x was approaching. Our next one is our second example from above. What would be the limit as x approaches c of just x Well, we said you could just plug that c right in. So this is going to give you c right back again. So in other words, the limit of x as x approaches 2, if I plug in 2, this must equal to 2. And then for our power functions, we said again, you could plug in that c, so the limit as x approaches c of x to the n is just c to the n. So if we talk about an x squared function with x approaching 2, if I plug in 2 for that x and then square it, this would just be 4. Okay, now what we're going to do is talk about some more properties of limits, and we're going to expand on our function and try to make it a little bit more complicated. So again, we're going to assume that b and c are constants that are any real numbers. We're going to let n be a positive integer, and we're going to let f and g be two functions with the following limits. And let me say one important thing here. These properties of limits do not apply if the limit of f and the limit of g do not exist in the first place. So they have to have actual limits for you to be able to apply these 5 different rules. So the limit of f as x approaches c, we're going to call that L, and the limit of g as x approaches c, we're going to call that K. So assume that L and K exist. Then our first property of limits deals with what we call a scalar multiple. A scalar just means a constant, a real number. And that's what this b is right here. That's called your scalar, and we're multiplying it by our function f of x. And what this property of limits says is you can essentially pull that scalar, that constant, out, find out what the limit of the function is first, and then multiply that by your constant b. So if we know that the limit of f of x is L, then I can just multiply that by b, and that will be the limit of the scalar multiple. So the limit of a scalar multiple is that scalar times the limit. The next limit law here is the limit of a sum or a difference. And what this says is that the limit of a sum is the sum of the limits, a limit of a difference is the difference of the limits. In other words, find the limit of f first, which we are calling L, find the limit of g second, which we're calling K, and then either add those or subtract those depending on the problem. So again, the limit of a sum or a difference is the sum or difference of the limits. It's very similar for the product. The limit of a product is the product of the limits. So first you find the limit of f, which is our L, then you find the limit of g, which is your K, and then you multiply those together. Again, very similar, a quotient rule here says the limit of a quotient is the quotient of the limits. So we're going to find the limit of the numerator, which is our f, and that goes to L, and then we're going to find the limit of the denominator, which is our g, and that goes to K. Now there's one little exception to this rule. We are going to say that this is only true as long as K does not equal to 0. Otherwise, we would be dividing by 0, and this would be undefined. Okay, our last limit law here is the limit of a function raised to a power. What we get to do is take the limit of just the function itself and then raise that answer to our power. So if the limit of f is L, then our limit of our function to a power would just be L to the n. So on this next example, I'm going to apply these limit laws. I'm going to kind of do this example in the long way, and as you get more proficient at limits, you wouldn't need to show all of these steps. But I just want to show you how these limit laws are actually working on this example. So this is just a basic cubic polynomial, and we're going to break it down into all little tiny pieces and apply the appropriate rules as we go. So if I wanted to find the limit of this difference and this sum, the first thing I could do is break it up into the sum or the difference of the limits. So that would look like this. This limit becomes the limit as x approaches 3 of the 2x cubed minus the limit as x approaches 3 of the 3x plus the limit as x approaches 3 of the 1. So I took the limit of each individual term. Now this 2 is a scalar multiple which can be brought out, and this 3 is a scalar multiple which can be brought out. So this becomes 2 times the limit as x approaches 3 of our x cubed minus 3 times the limit as x approaches 3 of our x plus the limit as x approaches 3 of our 1. And then each of these individual limits right here, here, and here come from that very first page of notes that we talked about. This x cubed is just a power function, so we should be able to plug in 3 and then cube it. So this limit goes to 3 cubed, but we have to multiply it by that scalar of 2 out front. The limit of x as x goes to 3 is just 3. That was also from our first page of notes. And then we're going to multiply that by our scalar. And then this last one is the limit of a constant is the constant right back again. So the limit of 1 is just 1, regardless of what x approaches. 3 cubed is 27. 27 times 2 is 54. Minus 9 plus 1, that's going to give us 46. Now note, to avoid all these extra steps here, you can recognize that this is a nice polynomial, and what we're going to be able to see is that if I had just plugged in 3 from the very start into this polynomial, we would have gotten that 46 as well. So this is a theorem. It says that the limit of a polynomial can be found by just doing direct substitution. So direct substitution is valid for finding limits of all polynomial functions. So if you have a polynomial p of x, then to find its limit as x goes to c, just plug in c for that x. So this is going to save us a lot of time. We won't need to make tables and we won't need to make graphs if we're working with a polynomial. We can just plug in our limit value and we'll have our answer right away. Another theorem is the fact that direct substitution is also valid for finding limits of rational functions. And a rational function means a fraction, a polynomial p of x divided by a polynomial q of x. So if we wanted to find the limit of that p of x over q of x, all we have to do is substitute in c for these two x's. So this is going to be p of c over q of c. And that's valid as long as that denominator does not become 0. Otherwise, you'd be dividing by 0 and that wouldn't work. Okay? So for example, if I wanted to find the limit of this rational function right here, it's a polynomial over a polynomial. So all I have to do is plug in 1 for all these x's and see what we end up with. So I would get 1 squared minus 1 minus 2 over 1 cubed plus 2. So that's 1 minus 1 minus 2 over 1 plus 2. 1 minus 1 goes to 0. So this is negative 2 over 3. And that doesn't have a 0 in the denominator. So the limit does exist. And it equals negative 2/3. Okay, another couple of theorems that are going to be useful for us. Direct substitution is also valid for finding limits of all radical functions, given that the radical is defined at c. So if you want to find the limit of the nth root of x, all you have to do is plug in c, and you would get the nth root of c, as long as that is defined. And if your root is an odd root, like a cube root or a fifth root, then this will always be defined. But if you're dealing with even roots, like square roots and fourth roots, if this c was something negative, then that would be undefined. So you just want to make sure that you're dealing with things that are defined. So for example, the limit of the cube root of x, as x goes to negative 27, I can plug that in. It's okay to take an odd root of a negative that does exist. The cube root of negative 27 would just be negative 3. So there's my limit. And then if I want the limit of the fourth root of x, I can plug in 16 for that x, and the fourth root of 16 does exist and is just 2. Okay? Another theorem, the limit of a composite function. Composite functions are functions that are inputted into each other. So you have two functions, an f and a g, and the composition of f with g would be g inside of f. G becomes the input of f. Now, in order for this to work, you need the limit of g to exist and equal L as x approaches c. Then you need the limit of f to exist as x approaches L and equal to f of L. So the way this would work is you would essentially substitute in your c in for that x, if that exists and that limit exists, and in this case we're saying that that is going to L in the limit, so then the limit of f would go to f of L. So in other words, if you have a more complicated function that looks kind of like a function within a function, like this next example, you should be able to plug in, as long as each piece exists, and get your final limit. So this is like a quadratic polynomial inside of a square root. So the first thing we're going to do is we're going to try to find the limit of this inner function by just plugging in, which we should be able to do because it's a polynomial. So 2 times 3 squared minus 3 times 2. Now that should exist, so if it does, then I should be able to take the square root of that and get my final answer. Well, 3 squared is 9, 9 times 2 is 18, and, whoops, this should be a 3 here. 3 times 3 is 9, and 18 minus 9 is 9. That exists, square root of 9 does exist, and is equal to a positive 3. So for a lot of these functions, we're just using basic direct substitution. Okay, one more theorem here, and this is for limits of trigonometric functions. So let's see be a real number in the domain of a given trigonometric function. In each case, direct substitution is valid for finding the limit of the given trig function. So in other words, we can just plug in our c and we will have our limit. So if I want the limit as x approaches c of sine of x, then this would just be sine of c. The limit of cosine becomes cosine of c. The limit of tangent becomes tangent of c. Limit of cotangent is cotangent of c. Limit of secant is secant of c. And limit of cosecant is cosecant of c. Now this assumes that when you plug in that c value, you get a value that actually exists. And for some of these functions like tangents, cotangents, secants, and cosecants where you have division involved, those might potentially become undefined if you're dividing by 0. So you have to be careful. So for example, what would be the limit as x approaches pi over 2 of sine of x? Well, it should be whatever sine of pi over 2 equals, and on a unit circle, pi over 2 is 90 degrees, then sine of pi over 2 or 90 degrees is just a 1. What's the limit of cosine of x as x goes to pi over 6? Well, that's cosine of pi over 6. That's the same as 30 degrees. And on a unit circle, remember the cosine is the x value, and the terminal point of pi over 6 is root 3 over 2 comma 1/2. So the x value is the root 3 over 2. You do need to have these unit circle values memorized. Finally, the tangent of x as x goes to pi over 4 would be the tangent of pi over 4. The terminal point of pi over 4 is root 2 over 2 comma root 2 over 2, and tangent is y over x. So when you take root 2 over 2 and divide it by root 2 over 2, it cancels out to a 1. So this is just 1. Now suppose that we have two mysterious functions, f and g, that we don't have formulas for, but we do know a limit. We know that the limit of f as x approaches c is 2, and the limit of g as x approaches c is 4. Based on just those two pieces of information, we're going to find each of the following limits using our limit laws. So the limit as x approaches c of 4 times f of x, that's that scalar multiple rule. We're allowed to pull this 4 out and multiply the limit of just the f by 4. And the limit of f, according to what we were given, is 2. So 2 times that 4 makes this whole thing 8. Okay, so that's that scalar multiple law. The next one here is our sum law. The limit of a sum is the sum of the limits. So this is going to become the limit of just the f plus the limit of just the g. And f in the limit goes to 2, g in the limit goes to 4, so the sum of those two things will be 6. Okay, the next one is a quotient. So the limit of a quotient is a quotient of the limits. So this becomes the limit of the numerator over the limit of the denominator. The limit of the numerator, the limit of f, goes to 2, and the limit of 4, that's just a constant. So the limit of a constant is the constant right back again. So we get 4 right back again. 2/4 reduces to 1/2, so that's our limit. The limit of the cube root of f of x. So our radical law says that we can, or our power law says that we can take the limit of just the f of x part and then take the cube root of that answer, assuming that the limit of f exists, which it does. It goes to 2, so this is just going to end up being the cube root of 2. And here's our power rule again. The limit of f of x squared would be the limit of just the f of x part, and then you square that answer. So since f of x goes to 2 in the limit, 2 squared goes to 4. So we now have lots and lots of limit laws that will help us find limits very easily, and basically they all are just a result of direct substitution. However, the more interesting cases in calculus are the ones where direct substitution doesn't work. So that's what we're going to talk about next. We're going to look at limits that cannot be evaluated using direct substitution. So let's look at the function f of x equals to x squared minus 3x all over x. Now, according to our limit theorem for rational functions, this is a polynomial over a polynomial. So I should be able to use direct substitution by plugging in 0 into the top and into the bottom. But notice what happens when I do that. I get 0 squared minus 0, which is just 0 on the top, and on the bottom I get 0 as well. This means we can't use our limit law because we ended up with a 0 in the denominator. Not only that, we also have a 0 in the numerator. This is a very special form in calculus called an indeterminate form. And a lot of times in math we think, oh, as soon as you see a 0 in the denominator, this doesn't exist and is undefined. But the thing about an indeterminate form is that sometimes this does exist. If you have 0 over 0, sometimes this does actually have a limit. We have to just be a little bit more creative and careful about how we go about getting it. Okay, so 0 over 0 means we're going to have to pull out our bag of tricks and see if we can figure out a better way to get an actual answer. So the trick that we're going to pull on this example is to notice that this numerator in our function f factors. I can factor out an x from both of these terms, leaving me with x times x minus 3. And the fact that I have an x in the top and in the bottom means that those should simplify by canceling out, leaving me with this new simpler function x minus 3. Let's call this linear function x minus 3 g of x. Okay? Now f of x was this original fraction. So what's the difference between f and g? It appears just from algebra alone that they are equal to each other, but there is one slight difference. And the fact is that these are the same except wherever that denominator was going to equal to 0, which in this case is at 0 itself. So these are the same except at x equals to 0. And we have talked about this before in a previous lecture. When you have problems like this that reduce, you have in the original graph of f a hole showing up at x equals to 0. So f of x will look exactly like g of x, but f of x will have a hole at x equals to 0. So let's draw these two graphs so that we can see. G of x is just this x minus 3 function, and that's just a line. It has a y-intercept at -3, and it has a slope of 1. So it's going to look something like this. Just a nice line. F, on the other hand, was that rational function. So what does its graph look like? Well, it looks exactly like the graph of g, except you're going to have a hole at x equals to 0. Now x equals to 0 would normally be this y-intercept. So instead of having a nice solid dot there, on the graph of f we're going to have that open circle. And then the rest of the graph will look just like our straight line. So f and g are functions that agree everywhere except at one point, except at 0. And what we're going to see in this next theorem is that if you have two functions that agree everywhere except one point, then they have the same limit at that point. So let c be a real number, and let f equal to g for all x except for at c. So c is the bad point where they don't match. If the limit of g as x approaches c exists, then the limit of f of x also exists and equals to the limit of g. So what that means for our example up here is that if we find the limit as x approaches 0, that bad point of our function g, what would that equal? What's the limit of x minus 3 as x approaches 0? Well, if I plug in 0, which I can do because this is just a polynomial, we would get negative 3 for an answer. So the limit of g is 3. Excuse me, negative 3. What would that mean the limit of f is? Well, here's the notation for it. The limit as x approaches 0 of this rational function equals the same thing as the limit of x minus 3, that reduced version of it after we cancel out the x's, and that is equal to negative 3. So in other words, the limit of f also equals negative 3. And we can see that graphically because we talked about this when we talked about how to graphically find limits. Imagine two cars driving along this curve. We said graphically that limits do not care about holes. These two cars do want to crash even though there's a hole right there, and the height at which they want to crash is at negative 3. So that's why the limit of f is also equal to negative 3. Okay? So limits don't care about holes. So what we're going to do next is use that theorem to manipulate limits that we might think don't exist. We're going to turn them into functions that do have limits, and we're going to equate the two together. So, for example, here was that function f that we were just talking about, and here's how you would formally write it up. This becomes the limit as x approaches 0 of x times x minus 3 all over x. The x's cancel out, giving me a simpler function, just that x minus 3, which does have a limit at 0. If I plug in 0 right here, we're going to get 0 minus 3, which is negative 3. So the limit of the original function up here is negative 3. And the trick that we used here was factoring. We factored the numerator, canceled out some x's, so that we were left with something simpler that did have a limit. Now, if we go to this next example, we might initially think that we should factor here as well. But what I want you to remember before you do anything else is that you always want to plug in your limiting value first to see what you're dealing with. So let's go ahead and do this. This is a polynomial over a polynomial. So we can try direct substitution. If we plug in 0 for x in the top, we get 0 cubed plus 1, which is just 1. And on the bottom we get 0 plus 1, which is just 1. And lo and behold, 1 over 1 equals to 1. We did not get an indeterminate form. So the fact that we could just plug in and get an actual number for an answer means we're done. You don't need to do any special fancy tricks here. Just plug it in. As long as you don't end up with 0 over 0, you're good to go and you have your answer. So let's try another one here. The limit of 2 minus x over x squared minus 4 as x approaches 0. So the first thing you want to do is plug in that 0 and see what you're dealing with. If I plug it into the numerator, I get 2 minus 0. On the bottom, I get 0 squared minus 4. So this reduces to 2 over negative 4, which is negative 1/2. We didn't get 0 over 0. We didn't get that indeterminate form. We got an actual number. So this limit does exist, and its value is -1/2. Now if I take that same function, but I change the value at which x is approaching, this time I'm going to let x go to 2. Let's try our direct substitution. 2 minus 2 on top is going to go to 0. 2 squared minus 4 is also going to go to 0. So this is that indeterminate form. When you are presented with that, that's when you have to think about doing something special, doing some kind of trick. And if I look at this function that I was given, the trick to try here is that factoring again, because that denominator has the look of a difference of squares. So there's very good potential that we can factor and maybe cancel out something in the numerator. So let's try that. I'm going to leave the top the way it is, and I'm going to factor the denominator. It becomes x and x, 2 and 2. One of these is plus and one of these is minus for a difference of squares. Now normally we would like to see exactly the same thing on top and bottom, and we don't have exactly the same thing on top and bottom, but we're really close. You need to remember that 2 minus x and x minus 2 are opposites. So you do get to cancel them out, but because they're opposites, they don't cancel to a 1, they cancel to a -1. So what we're left with after we cancel is that -1. I'm just going to put it in my numerator, and on the bottom just that factor x plus 2 that was left over. After you've done that canceling step, you should be able to plug in your 2 now and get your final limit. You should be left with something simple enough that does have a limit. So if we plug in 2, in the bottom we get 2 plus 2, and this gives me -1/4. So my final limit here is -1/4. Okay, the next example here. Limit as x approaches 0 of square root of 2 plus x minus square root of 2 all over x. Now first things first, always plug in your 0 right away to see what you're dealing with. So if I plug in a 0, 2 plus 0 is going to stay 2. So this is square root of 2 minus square root of 2, which is 0. And on the bottom, when I plug in 0, I'm going to get 0. So we are getting that indeterminate form. So that's when we have to try something tricky, okay? So in this problem, factoring probably won't work because nothing in this problem looks like something I know how to factor. What it does have in it are radicals. And there's a nice trick to try when you're dealing with radicals. It's called multiplying by the conjugate. Now what is a conjugate? A conjugate is an expression that's extremely similar to the numerator that we have already. I'm going to use the numerator because that's the part that has the radicals in it. And the conjugate will look exactly like this, except this middle sign becomes the opposite. So instead of subtraction, I would use addition. So here's what this problem is going to turn into. We're going to take the limit of our original problem, and I'm going to multiply this by a fraction. And the fraction is going to be the conjugate of this numerator, which is square root of 2 plus x plus square root of 2. And I also have to multiply by that in the denominator as well. This fraction that I'm multiplying by right here is really just a fancy version of 1. So that means we're not changing the problem. It would be like saying that 1/2 multiplied by 2 over 2 becomes 2/4. 1/2 and 2/4 are the same fraction. They're just in different forms. And that's what we're doing here. We're trying to take this original fraction and turn it into a different form that is actually easier for us to work with. So let's see what happens. Now when you're multiplying by a conjugate, I strongly encourage you to use parentheses around all of these terms that have pluses and minuses, because that's going to help remind you that you do need to FOIL and that you do need to distribute. Now when I distribute on the top, please notice that you do have a difference of squares pattern. These two expressions in the parentheses are identical, but they have opposite signs. So when I FOIL, the inner term and the outer term are going to be exactly the same but opposite signs. So that means they're going to cancel out every time, and that always happens when you're multiplying by a conjugate. Your inners and your outers will be identical but opposites, so they cancel out. So I'm not even going to bother multiplying and writing that out because I know that they're going to cancel automatically. What will still be around is the first times the first and the last times the last. So let's look at those. What would be the first times the first? Square root of 2 plus x times square root of 2 plus x. Well, square root of 2 plus x times square root of 2 plus x is square root of 2 plus x squared, and a square root cancel out, giving me just that 2 plus x without the radical. So no more radicals at all. Now if we do the last times the last, what is square root of 2 times square root of 2? That's like square root of 2 squared. The square and the square root cancel out, giving me just the 2 without the radical. A minus times a plus is going to make this minus. So that's what my numerator should look like. You shouldn't have any radicals left at all in the top because those inners and outers will cancel out and the first and last will square away the radical. Now in the bottom, I would strongly recommend that you don't distribute, and I'll show you why. So in the bottom, do not distribute your x across, leave it out front, and leave this conjugate in your parentheses. In my next step, let's simplify the numerator. The 2 and the minus 2 should cancel out, leaving me just an x on top. And that's why I don't want you to distribute in the bottom, because the x that's left over in the top should cancel with the x that's in the bottom. And that will always happen if you're doing these problems correctly. Now when you do that canceling step across the top and the bottom, that should always be the sign that you're now ready to plug in and get your final answer. Let's see what we're left with here. If I cancel out those x's, I have just a factor of a 1 left on the top, and I have that conjugate left on the bottom. I should be able to now plug in 0 for that x. So if I do that, I'm left with 1 over square root of 2 plus 0 plus square root of 2, and that's just square root of 2 plus square root of 2. And remember, root 2 plus root 2 is like an apple plus an apple, gives you 2 apples, so this is going to be 2 root 2's. Now I am fine with you leaving radicals in your denominator. However, your textbook probably wouldn't leave this answer the way I have it written if you're checking your answer in the back of the book. It would rationalize. So let me just show you how you would do that. You would multiply top and bottom by square root of 2 over square root of 2. 1 times root 2 is root 2. And then in the denominator, root 2 times root 2 is 2 times the 2 that was already there, so this becomes a 4. So either your answer should be 1 over 2 root 2, or if you decide you want to rationalize, it would be square root of 2 over 4. I personally don't care about the radical in the bottom, but you should know how to go back and forth so that when you're checking your answers, you'll know if you got it right or not. Okay? So when you have a limit involving radicals that starts out as an indeterminate form, the strategy to try for that is to use a conjugate and multiply the top and the bottom by the conjugate of the expression that involves the radicals. Okay? Let's try another example. This one is a complex fraction. It has fractions within fractions. So if we go and we try to plug in our 0 right away, 0 plus 4 would be 4. So this is going to be 1/4 minus 1/4, which is 0. And if I plug in 0 in the bottom, I'm going to get 0 back again. So there's that indeterminate form. That's when you have to pull out your bag of tricks. Now this one doesn't really have any potential for factoring, and the fact that there's no radicals in it means we probably can't use a conjugate either. So the strategy that we're going to try whenever fractions are involved is to get a common denominator. and we're going to multiply by that common denominator on the top and the bottom, just like we did with our conjugates. So what I'm going to do is I'm going to take this original function and I'm going to multiply it by our common denominator. Now in the original fraction, I have an x plus 4 in my denominator and I have just a 4 in my denominator. So your common denominator needs to be these two guys multiplied together. So you need a 4 and you need an x plus 4. And to keep it balanced and equivalent, I'm going to multiply by that in the denominator as well. Okay, so we're multiplying top and bottom by 4 times x plus 4. Now let's see what happens when we do that. When I take this fraction times my common denominator, the factor x plus 4 is going to cancel out with the 1 in the denominator, and it's going to leave me with this 1 times this 4. So we just get 4. No more fractions are left over. Now if I go and I multiply this 1/4, whoops, sorry about that. Now if I multiply this 1/4 times my common denominator, this time the 4's cancel out and I'm left with 1 times x plus 4. Now this is very, very important. Leave that x plus 4 in parentheses because we have this subtraction in between, and you're going to need to make sure you distribute that negative in the next step. Now in the bottom, just like with the conjugates, you don't want to try distributing that x across. It's better to just group all three of these next to each other, and you can put them in any order you like. I like to put the 4 first, then the x plus 4, but it doesn't really matter what order you have them all in. Just make sure they're all accounted for. So don't distribute on the bottom, because in the next step we're going to distribute this negative across, and that's going to give me 4 minus x minus 4, which means the 4 and the minus 4 cancel out, giving me the limit as x approaches 0 of a negative x over 4x times x plus 4. Now here's the step that we're looking for. If you're doing these right in all of these limit problems involving indeterminate forms, you should always get to a point where there's a factor on the top that cancels the factor on the bottom. In this case, it's that x. This x and this x should cancel each other out. And that means we're going to be left with a negative 1 on top. Don't lose that negative. You still have your 4 in the bottom and your x plus 4 in the bottom. As soon as you've canceled those x's, you should be ready to plug in your 0 for this x and get a number. We're going to get negative 1 on top, 0 plus 4 is 4, and 4 times 4 is 16. So my final limit is negative 1/16. Okay? Alright, let's try another one. Now this one has radicals, but don't jump the gun. If you see a radical in your problem, don't immediately think that you need to use a conjugate. Remember to always plug in your limiting value first to see what you're dealing with. So if we plug in 0, this is going to become square root of 0 plus 1 minus 2 over 0 minus 3. Square root of 1 is 1. 0 minus 3 is negative 3. And 1 minus 2 is negative 1 over negative 3. The negatives cancel out. And I got a number. I didn't get 0 over 0, so I don't need to use a conjugate at all. If you tried using conjugates, you would create a whole lot more work for yourself than if you had just checked it right from the beginning by plugging in that 0. So don't forget to plug in first. Okay, the last example here looks like this. We have two variables involved, x's and h's, and we want the limit as just the h goes to 0. And we have x plus h quantity cubed minus x cubed all over h. Now just like in all the other problems, you want to plug in first. But be careful here, because there's two variables, you're just plugging in 0 for the h's. So I'm going to put a 0 here and a 0 here. And that would leave me with x plus 0, or just x, quantity cubed, minus this x cubed all over 0. And that's obviously going to be a 0 over 0. So we have an indeterminate form. So far our strategies are to factor, or to use a conjugate, or to use a common denominator. We don't have radicals and we don't have complex fractions, so we probably don't want to use conjugates or common denominators. You could possibly try and see if this could factor, but what we're going to do instead is use a new technique, and that is to just expand it out. In other words, FOIL. When you see parentheses in the original problem, like I see right here, I am going to actually FOIL all of that out and hope that something cancels with this x cubed. And that should hopefully give me something that I can work with. Now, there is a pattern that you should have memorized from intermediate algebra for how to cube a quantity. If you don't remember what the pattern is, then your only other alternative is to go ahead and FOIL x plus h times x plus h, get that answer, and then multiply that answer by another x plus h. I'm not going to show all that work. I'm going to just write down what the final pattern turns out to be. And this is something I would highly recommend you memorize so that you don't have to go through all this work. So here's what we get. When we cube out x plus h, we get an x cubed for the first term. We get a middle term that has a coefficient of 3, and it's going to have an x squared and an h. And we get another middle term with a coefficient of 3, which has just an x and an h squared, and then the last term is that h cubed. To help you memorize the pattern, notice that the two middle terms have coefficients of 3's. The powers on the x's go down, 3, 2, 1, 0, and the powers on the h's go up, 0, 1h, 2h's, 3h's. So that's kind of how I remember it. So these four terms are this quantity expanded out. I still need to subtract from this that other x cubed on the end. And then I have h on the bottom. Now the good news is these x cubes cancel, which leaves even better good news, because what we're left with on the top, every single term on the top has an h in it, which means it has a GCF that I can pull out. So I am going to factor out an h from my numerator. If I pull out this h, I'll be left with 3x squared. If I pull out one of these, I'm left with a 3xh. And if I pull out one of these, I'm left with an h squared. Remember, when you're dealing with these indeterminate forms, you're looking for that cancellation step, and here it is. The h that we have on the top cancels with the h that we have on the bottom. And what we're left with should now be something that we can plug into and get our final answer. Now you have to be a little bit careful here because we are dealing with two variables. Oops, I just realized I made a typo here, and it's going to affect our last step. This is what you want to be careful about. We want the h only to go to 0. In this problem, even though there were x's and h's, we're not dealing with the x, we're letting the h go to 0. So this 0 goes in for that h, and this 0 goes in for that h. So what we would be left with is 3x squared, we're not plugging anything in for the x, plus 3x times 0 plus 0 squared. This goes to 0, this goes to 0, so what we're left with is a 3x squared. And even though that still has an x in it, that's our final answer. On this particular example, we don't end up with just a constant. We end up with a function. Okay? So strategies for dealing with indeterminate forms: try factoring, or try expanding, try multiplying by a conjugate, or try multiplying by a common denominator. Okay? Now the next theorem that we're going to talk about is called the Squeeze Theorem. And this theorem is useful in helping to prove a lot of important theorems in calculus, and we're actually going to use it to prove a theorem in just a minute. But let's talk about what the Squeeze Theorem says first. What you have to start off with is this relationship between three functions. You're going to have a function f that lies between two other functions. So f is greater than or equal to a lower function h of x, and f is smaller than an upper function g of x. And you can use this picture to help visualize. So you have this upper function g, and you have this lower function h, and then you have this other function f, which is always in between them. So here's what the Squeeze Theorem says, and you can see it visually from the graph. If the limit of g goes to L, and the limit of h exists and goes to L, then the limit of f, because it's being squeezed in between these two other functions, would also have to exist and go to L as well. So that's what this theorem says right here. If f is between h and g, and the limit of h is equal to L, and the limit of g is equal to L, then the limit of f has to equal to L. So we're going to use that theorem to prove the following limit. And this limit is a very important one that we use quite often in lots of examples coming up next. So we want to find out what the limit as x goes to 0 is of sine of x over x. And to find this limit, we're going to start by drawing a unit circle, which is just a circle centered at the origin with a radius of 1. So this distance right here is 1, and this radius right here would also be 1 as well. Now because we're on a unit circle, you should remember this from trigonometry, every terminal point on a unit circle has coordinates cosine theta for the x and sine theta for the y, where theta is this central angle being measured from the positive x-axis up to this ray. Now, we're going to find out a couple of other points as well. Let's find the coordinates of this point. We know that we go over 1 unit to get to that point, so the x-coordinate would have to be a 1. But what would the y-coordinate have to be? Let's call this height y. And what I want you to notice is we can use a little trigonometry here for this right triangle. This is a right angle right here. And according to our trigonometric functions, tangent of theta, so tangent of this angle, is opposite over adjacent. And the opposite side is our y, and the adjacent side is this 1 down here. So if you realize that that relationship is true, then that forces y to be tangent of theta. So this height right here is tangent of theta. Okay, and we'll need that information in our proof. So here's what we're going to do. We're going to notice a little relationship. Take a look at these 3 pictures. We have this tall triangle right here, and the area of that big triangle is obviously bigger than the area of just this little wedge, what we call a sector, this little pie piece. So the area of the big triangle is bigger than the area of the sector, but the area of the sector is bigger than the area of this little inscribed triangle right here. So you can see that this little tiny piece right here is left out. We're taking out this little wedge right here from the sector. So the area of this inscribed triangle would be smaller than the other 2. So that's going to give us kind of a relationship that we're going to use, and we're going to use this to help us employ that squeeze theorem. So let's go ahead and see if we can come up with some formulas for what these 3 areas would have to equal. So this first big triangle has a base of 1 right here and a height of tangent of theta, and that's what we came up with earlier. And since the area of a triangle is 1/2 base times height, then this would be 1/2 the base, which is 1, times the height, which is tangent of theta. Now that area has to be bigger than the area of the sector, that little pie wedge. Well, what's the formula for area of a sector? This is again something that you would learn in trigonometry. It's 1/2 the radius squared times theta. So in our problem, this would be 1/2. The radius is 1 because we're on a unit circle, and our theta would just be theta. Then finally we get to our smaller triangle. Okay, so if we take a look at this smaller triangle, just this one outlined in red, we need a base and a height for this. Well, the base would be down here, which is 1. And now we need a height, which is this vertical distance right here. I'll call it h for now. Now to figure out what that h is equal to, we're going to use, again, a little bit more trigonometry. This right triangle right here has a hypotenuse that's equal to 1 because that's this radius that goes up through our unit circle right here. So this hypotenuse is 1. So if we look at this smaller little triangle on the left, let me use a different color so you can see. We look at this little right triangle on the left side. The hypotenuse is 1, the height is h, and a trig relationship that we could use is sine of theta, which is opposite side over hypotenuse. And the opposite side of this right triangle from theta is h, and the hypotenuse is that 1. So this tells me that my height, h, is sine of theta. So let's put it all together. The area of this triangle, which is smaller than the area of our sector, is 1/2 the base, which is this 1, times this height h, which we just found out is sine of theta. So here's our bounded areas, okay? Big triangle, sector, small triangle. Now let's clean this up just a little bit. This one right here, I can think of this as tangent of theta all over that 2. The one in the middle, 1 squared is 1, so this is just theta over 2. And on the right-hand side, this becomes sine of theta over 2. So what I want to do next is I'm going to kind of clean this up a little bit. And you probably wouldn't think to do this on your own. That's why these proofs are hard. But what we're going to do is we're going to multiply all 3 pieces by the reciprocal of this sine of theta over 2. So we're going to multiply by 2 over sine theta. So we're going to multiply this guy by 2 over sine theta. We're going to multiply this by 2 over sine theta. And we're going to multiply this by 2 over sine theta. And as long as we're multiplying every piece of that inequality by the same thing, it stays equivalent. So we're not changing the accuracy or truthfulness of this statement. Now let's clean it up a little bit. Here the 2's obviously cancel. Remember that tangent of theta is sine theta over cosine theta. So the sines also cancel. And what we're left with then is just this cosine, but look at where it is. It's in the denominator. So this becomes 1 over cosine theta. In the middle, the 2's cancel, and we're left with that theta on top and that sine of theta on the bottom. And on the right-hand side, the 2's and the sines cancel, so we're left with just 1. Okay, now the next step that we're going to take is we're going to take reciprocals. Again, this is probably not something you would necessarily think to do on your own. That's why the proof is hard. I just want you to be able to follow the steps, not necessarily think of each step on your own. Okay? Now, one thing we need to worry about with reciprocals. When we flip these guys over, that's what reciprocal means. This would become cosine theta. This would become sine of theta over theta, and the reciprocal of 1 stays 1. The problem with taking a reciprocal is it affects the inequality. And let me just give you a very simple example. Think about 1/4 compared to 1/5. We know that 1/4 is bigger than 1/5. What happens when I take the reciprocal of each of these? This becomes 4 and this becomes 5. Should this stay a greater than symbol? Is that still true? Is 4 greater than 5? No, it's not. You have to flip the inequality around to maintain the truthfulness of the inequality. So when you take a reciprocal, you have to flip as well. So in other words, this greater than or equal to flips into a less than or equal to, and this greater than or equal to flips into a less than or equal to. All right, we're almost where we want to be. We did a lot of manipulations here to get this function in the middle. Remember what we were trying to do in this original problem. We are trying to find the limit of sine of x over x, and that is now what I have in the middle. I have that f of x function in the middle. This is the lower function, that h of our squeeze theorem, and this is our upper function g in our squeeze theorem. So now what we're going to do is we're going to apply the squeeze theorem. And we're going to take the limits of all three of these as theta goes to 0. So I'm going to take the limit as theta goes to 0 of the left function. That has to be less than or equal to the limit as theta goes to 0 of the middle function, and that has to be less than or equal to the limit as theta goes to 0 of 1. So let's find out what these go to. What's the limit of cosine of theta as theta goes to 0? Remember that you're allowed to use direct substitution here. So if I plug in a 0, this is cosine of 0. And what is the cosine of 0? It's 1. Now go to the other side. What's the limit of 1 as theta goes to 0? Well, 1 is a constant, and the limit of a constant is that constant right back. So the limit of 1 is also 1. So what does that force the limit of this middle function to be? If it has to be between 1 and 1, then it must be 1. So this tells us that the limit as theta goes to 0 of sine of theta over theta equals to 1. Okay? Now, that's something you want to have memorized. I'm going to go ahead and write it up here at the top of our next page because we will be using this in our examples coming up. I'm also going to generalize it into a slightly different form. This could also be thought of as the limit of sine of box over box as box goes to 0 equals to 1. And I'm going to tell you why we might want to think of it that way in a little bit. Some of the limit problems that we're going to do are not going to just have thetas or x's right here. You might have 2x or 3x or x squared or something like that. So if we change this expression where this box is, as long as you have that same expression in the top and in the bottom, and that expression is going to 0, then the limit will still be 1. So this is kind of like a generalization of this theorem. Something else that I want to point out is that the reciprocal of these two limits also is true. So if I flip this over and I take the limit as theta goes to 0 of theta over sine of theta, that is still 1. And if I take the limit as box goes to 0 of box over sine of box, that will still be 1. So these are all different versions of this same result that we just came up with. I'm going to add one more theorem to that list, this next problem, and then we'll put them all into action. Okay, so let's take a look at this limit. Let's find the limit as x goes to 0 of 1 minus cosine x all over x. Now to do this one, when you first plug in 0 to see what you're dealing with, you would get 1 minus cosine 0 over 0. Now cosine of 0 goes to 1, so 1 minus 1 is 0 over 0. We get that indeterminate form. So what do we do once we get that indeterminate form? We pull out our bag of tricks. Because there's this trig function in there that complicates things. This doesn't look like it's going to factor. There's no parentheses, so we can't expand. There's no fractions, so we can't use a common denominator. And it doesn't have any radicals, so we might think we can't use a conjugate. But actually, we are going to multiply by a conjugate here. Sometimes that conjugate trick still works, even if you're not dealing with radicals. So let me show you how it works in this example. So you take your original limit, and we're going to multiply it by the conjugate of this numerator, which will look exactly like this, but with a plus instead of a minus. So the conjugate of the numerator would be 1 plus cosine x. And I have to multiply that in the denominator as well to keep this balanced. Now let's see what this turns into. Remember that when you're multiplying by conjugates, you want to think in terms of using parentheses, okay? And use the fact that since you have conjugates in the top, the inner, which would be a minus cosine x, will cancel with the outer, which is a plus cosine x. So I'm not even going to bother to write those. The only terms that are going to end up mattering are the first times the first, which is 1 times 1, and that's 1, and last times last, which is a negative cosine x times a positive cosine x, which is a negative cosine squared x. Then on the bottom, we're left with that x and that 1 plus cosine x. Do not distribute that denominator. You don't want to do that. You want to leave it in its factored form. Now at this point, what you're left with doesn't look any better than what you started with. In fact, it actually looks worse. But you're going to use some trig identities to help you out here. 1 minus cosine squared x should look familiar. Remember that Pythagorean identity, sine squared x plus cosine squared x equals to 1. So if I were to subtract that cosine squared x to the other side, then this numerator is really the same thing as sine squared x. So I'm just going to do a little substitution. Alright, how did that help me? Well, it helped me because now I start to see a sine x on the top. There's actually 2 of those, and I have an x on the bottom. So that's kind of like this theorem that we just proved up here. Instead of thetas, I have x's. So this is like a sine x over an x. So what I'm going to do, and again, this is hard to think of on your own. It takes some practice with doing some problems and getting some experience to even think about doing what I'm going to do next. Here's what I'm going to do. I'm going to break up that numerator. Sine squared x is sine x times sine x. And I'm going to break up that denominator. I'm going to put the x under one of these, and I'm going to put the 1 plus cosine x underneath the other. So I haven't changed anything. It's still equivalent. I'm just breaking it up into pieces. And then what I can do to find the limit of this product is find the product of the limits. So I'm going to find the limit of the sine x over x, and I'm going to multiply that by the limit of the sine x over 1 plus cosine x. This guy is the theorem that we just proved. This goes to 1. This guy is basic substitution. If you plug in 0, you're going to get sine of 0 on top and 1 plus cosine 0 on the bottom. Sine of 0 is 0. Cosine of 0 is 1. So this is like 0 over 1 plus 1, which is 2. So that's just 0. So in other words, we are getting 1 from right here times 0. So the whole product goes to 0. So our final answer is that this limit goes to 0. So this is another one. It's probably not used quite as frequently as the sine x over x, but this is one you want to memorize. This goes to 0 because to try and reprove it every time is tedious. So if you just have it memorized, then you don't have to go through all those steps that I just did. So these two you want to have memorized. Okay, sine of x over x goes to 1, and 1 minus cosine x over x goes to 0. And we're going to use those to do some very common types of trig limits. So let's start with this first one. Find the limit, as x goes to 0, of sine of x over 3x. What you want to do is try and make use of some of these limit theorems that we've already proven, like the sine of x over x goes to 1. I see that right here. The problem is that 3. But 3 in the bottom is really like a 1/3 being multiplied by sine of x over x. Just separate that 3 and turn it into a scalar multiple. What do we get to do with scalar multiples? We get to pull them out. So this becomes 1/3 times the limit as x goes to 0 of sine of x over x. And this is our theorem. This goes to 1. When I multiply it by that scalar multiple, that makes the entire limit 1/3. As I said earlier, these take some practice. You might not initially think to do these steps the first time you do the problems, but because these problems are pretty common and they're usually in the same style and difficulty level as the ones I'm asking right now, you'll slowly get the hang of it. Now this next one looks very, very similar, but the 3 is in a different spot. And this is important to notice. That 3 is in what we call the argument of the sine function. There's implied parentheses right here. We want sine of the entire quantity 3x. Because it's next to that x inside of that sine, it is not a scalar multiple. This is not true. Sine of 3x does not equal 3 times sine of x. Just think of your double angle identities. Sine of 2x does not equal 2 sine x. It equals 2 sine x cosine x. Same principle at work here. So if you have a constant inside of your trig function, you're not allowed to pull it out. So what do? Well, this is where that box formula that I had up above comes in handy. Let me use a different color so that it stands out. Here's what we're going to use. The limit of sine of box over box still goes to 1 as long as these two expressions here match and that expression is still going to 0. So that's what we're going to try to turn this guy into. Since I'm not allowed to pull out that 3, then my box is 3x. And in order to be able to make this limit fit this formula, I need to have that same box out front here. So I really need to have a 3x. Is that what I had originally? No, I just had an x. So what we're going to do is we're going to multiply that bottom by 3 to make it match the numerator, but we have to balance this out still. You can't just multiply the bottom by 3, you have to balance it out by multiplying the top by 3 as well. Now that 3 that we're multiplying by on the top can go out front, or you can even pull it all the way outside of your limit, because that 3 is not inside of our box, it is a scalar multiple. So this 3 here and this 3 in the bottom are what are canceling each other out to keep this original to the original problem, but we're putting this into a new form so that we can apply our limit theorem. Now, is it true that if x goes to 0, then does 3x, in other words this box, still go to 0? Sure. If x is going to 0, then 3 times 0 will still go to 0. So we still have this box going to 0 as well. So we have all these pieces matching, and that means we're allowed to use our theorem. And what this theorem says is that this whole limit goes to 1 and gets multiplied by that counterbalancing 3 that we had to multiply by, so the final answer is 3. Okay, so that's a little bit tricky. We're going to do it again with another example that's even more tricky, but it's exactly the same idea. So on this next example, we have the limit as x goes to 0 of sine of 2x over sine of 3x. And again, you have to practice these to get the hang of them, otherwise you probably wouldn't think of what it's going to take to be able to do this problem. Here's what we're going to do. We're going to think of this as a box and this as a box. And we're going to use these two theorems. Sine of box over box goes to 1, and box over sine of box goes to 1. We're going to use those. So here's what I'm going to do. I'm going to break this up and I'm going to put sine of 2x, or sine of box, over something. I'm going to fill that in just a minute. And I'm going to take the sine of 3x and make that a box and put that in its own fraction. Now think about what we would need to have to make these fit these two patterns. I would really need to have a 2x here, and I would really need to have a 3x here. Unfortunately, we can't just put in things the way we want to. We have to make sure that things are balanced. So let's look at the x's first. Are the x's balanced? Have I multiplied by an x on the top and an x on the bottom? Yes, I have. This x and this x cancel each other out. So they are balanced, and I'm allowed to put them both in because I have one of each in each position. How about the 2? Is the 2 balanced? I put a 2 in the bottom, but do you see a 2 in the top anywhere to balance it out? No. So we need a counterbalancing factor of 2 somewhere in the numerator. It doesn't matter where. Now look at your 3. This is the 3 that I put in. Is it counterbalanced with a 3 somewhere in the bottom? No. So I need to put one in. You can put it wherever you want. I'm just going to put it underneath that 2. So in other words, we multiplied. What we really did here is we took sine of 2x over sine of 3x, and we multiplied this by a 2, by a 2 over 2, a 3 over 3, and an x over an x. And we just rearranged these in a specific way. So here's how I'm rearranging them. I'm putting the sine of 2x here, and the sine of 3x down here. I'm putting this 2 and this x down here. I'm putting this 3 and this x up here. And the leftover 2 and 3 I'm putting out front. So everything's been accounted for. I just rearranged everything to be in exactly the place that I want it to be. So now we should be able to use our theorems. This scalar multiple will stay there and be multiplied by whatever the limit of this and this is. Now this will go to 1 and this will go to 1 as long as the boxes go to 0, which will happen because if x is going to 0, then so will 2x, and if x is going to 0, so will 3x. So these limits do still apply. So my final answer is 2/3 times 1 times 1, which is just 2/3. Those counterbalancing fractions and constants are what I'm left with. So that's a little bit tricky, but if you think about what I did right here, I multiplied by 2 2's, 2 3's, and 2 x's, and then I just rearranged everything so that I had a 2x under my sine of 2x and a 3x over my sine of 3x, and then the leftover 2 and 3 are out front. Okay? So those take some practice. All right, let's try one more on this page. Let's find the limit as theta goes to 0 of tangent theta cosine theta over theta. So what we're going to do is, as we always do, plug in 0 first. And I should have done that on the last problem. I forgot to show that. But you'd get sine of 0 over sine of 0, which is 0 over 0. So that was an indeterminate form. So that's how we were kind of being creative here to get our limit. So let's try plugging in 0 into these. We would get tangent of 0 times cosine of 0 over 0. Tangent of 0 is 0. That comes from the unit circle. Cosine of 0 is 1. So 0 times 1 is 0 over 0. So it's another indeterminate form. So what are we going to do to try and make this work? Well, initially, I don't see anything that looks like a sine of theta over theta or sine of box over box. But I do know that tangent can be broken down into sine of theta over cosine theta. So that's what I'm going to do to try and get these signs involved so I can use one of these limit theorems that we've already proven. So here's what we're going to do. We're going to break down tangent of theta into sine of theta over cosine of theta. That's being multiplied by this cosine of theta on top, and we still have that theta on the bottom. Well, lucky for us, this cosine theta and this cosine theta will cancel out. So all we're left with is sine of theta over theta, and we're taking the limit of that as theta goes to 0. And that is our limit theorem, so this is just 1. So it was actually much simpler than we might have initially imagined. Okay, let's try the next example here. The limit as x goes to pi over 4. So the first thing I want to do is plug in that pi over 4 and see if I get an indeterminate form or not. So if I plug in pi over 4, I'm going to get 1 minus tangent of pi over 4. Tangent of pi over 4 goes to 1, and 1 minus 1 would be 0. So that's my numerator. On the bottom, sine of pi over 4 minus cosine of pi over 4 turns into root 2 over 2 minus root 2 over 2, so that also goes to 0. So we do have an indeterminate form. So what are we going to do? Well, here's the strategy. It's going to be the same exact strategy that we had on the last example. If you have one of these trig limits that involves a tangent, sometimes something that works well is to turn that tangent into a sine over a cosine and work from there. So that's what we're going to do. So I'm going to take this tangent and I'm going to turn it into sine of x over cosine of x. Now that doesn't seem to help too much because now we have a fraction within a fraction. We have a complex fraction. But that's actually good news for us because we have a strategy for how to deal with complex fractions, and that's to multiply this by a common denominator. And the only common denominator that I have here, the only denominator that I have, is this cosine x. So we're going to multiply the top by cosine x and the bottom by cosine x. So when I multiply the top, it will be this 1 times cosine x, which will still be cosine x, minus this sine of x over cosine x, which makes the cosines cancel, giving me just a sine of x back. In the bottom, remember not to distribute. I'm going to leave this guy in parentheses, and I'm just going to put that cosine of x next to it. And if you look carefully at the top and the bottom, these two factors here, they're not exactly the same, but they are opposites. So I do get to cancel them out, but I'm going to be left with that extra factor of -1. So we're left with -1 on top and cosine of x on the bottom. Once you've done that canceling step, you're usually ready to do your plugging in. So let's try plugging in pi over 4. So this becomes cosine of pi over 4. And cosine of pi over 4 is root 2 over 2, which is also the same as 1 over root 2, however you want to think about it. And 1 over root 2 flips it back over again. So this is really like -1, and instead of dividing by 1 over root 2, we could multiply by the reciprocal. So -1 times root 2 is -root 2. So there's my final answer. Okay? All right, next example. I see a tangent, so we may need to employ this same strategy of sine over cosine substitution, but before we do, let's plug in 0 and see what we're dealing with. So if I plug in 0, I get 3 cosine of 0 minus 2 over tangent of 0 plus 1. Cosine of 0 goes to 1, tangent of 0 goes to 0. So the numerator is going to be 3 times 1, or 3, minus a 2. That's a 1, and 0 plus 1 on the bottom, which is a 1. So the whole thing gives me just 1. I didn't get an indeterminate form, I got an actual number, so we're done. So that one was much easier. Okay, these last two examples that we're going to take a look at are going to employ that squeeze theorem again, and you probably wouldn't think to do that on this next example, but it just takes some practice and getting used to knowing what to look for. So on this one, the fact that I have a cosine in here instead of a sine, it doesn't look anything like sine of box over box. It doesn't look anything like that other cosine limit up here that we proved earlier means I have to try something kind of different. And I have a cosine instead of a tangent, so it's not even something that I could break down further. So that's when I'm going to think, well, maybe I could use the squeeze theorem here. And in order to use the squeeze theorem, I need to set up some sort of triple inequality. And here's the one thing that we know about the cosine function. Cosine, you all know what the graph of cosine looks like, hopefully. It looks like this. What is cosine always bounded between? It always is between -1 and +1. So cosine of any angle, namely cosine of 1 over x, for example, is always going to be bounded between -1 and +1, no matter what I pick for x. Cosine of anything is always between -1 and 1. That's always true by our unit circle. Now that's not quite this function that I'm trying to find the limit of. I've got the cosine part, but I'm missing this x out front. So what I'm going to do next is I'm going to multiply all three pieces by x. As long as you're doing it to all three, you're keeping that inequality still true. So x times -1 becomes -x. The middle becomes this function that I was trying to find the limit of. And the right side, 1 times x, becomes x. So here's where the squeeze theorem comes in. So by the squeeze theorem, the limit as x approaches 0 of this left function has to be less than or equal to the limit as x goes to 0 of this middle function, which has to be less than or equal to the limit as x goes to 0 of the right function. The one in the middle should be the one you're trying to find. The other two should be ones you should be able to figure out, and these I can just figure out by direct substitution. If I plug in 0, I'm going to get -0, the opposite of 0, which is still 0. If I plug in 0 on the right here, this limit is also 0. So that forces the limit in the middle to go to 0 as well by that theorem. So therefore, the limit as x goes to 0 of x times cosine of 1 over x must be 0. So the strategy here, since all my other strategies didn't seem to apply, was to use the fact that cosine, and this would also work for a sine function as well, cosines and sines are always bounded between -1 and 1. So I took that cosine function, bounded it between -1 and 1, and then I multiplied by that extra x that I wanted to have in my function. And then I took the limit of the left and the limit of the right, found that they were the same, so that forces the limit of the middle to also be 0. Okay, let's try that strategy one more time on this last example. This time I'm actually giving you that triple inequality, so the hard work is already done because I'm telling you what f is bounded in between. It's between b minus absolute value of x minus a and b plus absolute value of x minus a. So you don't even have to come up with that on your own. You can just jump right into that squeeze theorem. So by the squeeze theorem, since we have this function f that's bounded between a low and a high, the limit as x goes to a of the left function has to be less than or equal to the limit as x goes to a of the middle, which has to be less than or equal to the limit as x goes to a of the upper function. Now remember here, a and b are just constants, numbers. X is the variable. So when you take the limit of this left function, you're plugging in a for x right here. That's going to give you b minus absolute value of a minus a. That goes to 0, so this goes to b. Now go to the right function and plug in a. This goes to b plus absolute value of a minus a. That goes to 0. B plus 0 is b. So that forces this limit in the middle to be between b and b, which implies that the limit of f of x as x approaches a must be b. It has nowhere else to go because it's getting squeezed in between two functions that are going to be as you get closer and closer to a. Okay? All right, just to summarize, I'm not going to read through all of these, but this last page of notes here just lists all of our limit theorems that we've talked about today. And then on the very last page here, just a summary of all of our different methods for finding limits. You can find a limit numerically by making a table of values and picking x's that are really, really close to a. You can find a limit graphically by graphing your function and then looking to see if the cars would crash near x equals to a. Or you can find your limits algebraically by either just plugging in a if that works, or if you get an indeterminate form, use some algebra to simplify first and then plug in for a. And our strategies for dealing with an indeterminate form like 0 over 0 were things like factoring, either the numerator or the denominator, and then canceling out a common factor and plugging in, expanding or foiling to get rid of some parentheses and maybe cancel some terms out, multiplying by the conjugate on the top and the bottom. That's good for when you have radicals, or sometimes even if you have some trig functions, you can use a conjugate. Multiplying by a common denominator, especially when you have complex fractions. And then we had some of those trig strategies, converting tangents into sine of theta over cosine of theta, and see if that helps you to reduce. And then finally we had some limits that you want to have memorized. Things like the limit of sine of box over box goes to 1, or the reciprocal of that, box over sine of box goes to 1, or we had that same limit involving cosines, which isn't used nearly as much, but every once in a while you might see something of this form, and that limit went to 0. So you want to have those 3 versions memorized. Alright, it takes a lot of practice to do some of these algebraic limits that are indeterminate forms, so keep working at it and come and get some help if you have any questions. That concludes our lecture on evaluating limits algebraically with limit laws. Good luck.